Okay, thanks for coming. I'm thrilled and delighted to be here. Very interesting to be in Manhattan when they have 100% humidity and 92 degrees Fahrenheit. I'm not used to that. But all right, so I want to talk about visualizing quantum mechanics. Now, of course, I have specific interests, research interests of my own, but the general challenge of visualizing quantum mechanics is becoming more and more important as we try to develop more and more complex materials for more and more applications. That's the strategic context of this presentation. So please do just put up your hand, stop me, and ask questions. I'm going to show you a lot of different stuff, so it'd probably be more useful to ask me as something goes by than to try and have both of us remember 15 minutes later. Okay. So first thing I want to tell you is about electronic matter. Everyone in this room depends on electronic matter profoundly, either for their livelihood or their way of life, or both. So there are only three particles in our universe. There are two quarks, and there's an electron. Those are the only stable objects. Everything, you yourself, everything you've ever seen or ever will see, except for photons, are made of these three objects. So the quarks manage to bind, due to quantum mechanics, to make nucleons. The nucleons form the nucleus. Surrounding the nucleus are the electrons. And it's that quantum mechanical object which we call an element. And we have about 100 elements. Here they are. It's very, very surprising. If you told this to a 4-year-old, it's very surprising that you take 3 building blocks, and only 3, and you end up with this amazingly complicated set of objects which are stable in our universe. And of course, the reason why this is so is because of quantum mechanics. Quantum mechanics is approximately 100 years old, depending on who you want to give credit to. A little bit more if it's Bohr, and a little bit less if it's Schrödinger, but about 1 century old. It's the most fundamental theory we have of how our universe works. It's the basis for why we have all these extremely amazing elements made up of this very tiny number of constituents. So the basic theory of quantum mechanics, the simple wave theory, which is most relevant to what I'm going to talk about, says that every particle, every stable particle, is actually a wave. It's a matter wave. That's its wave function. It's a solution of a wave equation. It waves through space and time. Max Born proposed that the relationship of those waves to what we actually observe is that the probability of something occurring is the amplitude squared of the wave. You got to keep that in mind. We know of no way to make a machine to visualize Schrödinger waves, but I'm going to show you how to make a machine to visualize Schrödinger waves squared. That's a doable thing. So let's think of a real wave. It's a wave that you are largely made of. It's an electron wave. So an electron is a very small object, about 10 to the minus 30 kilograms. It's got a charge, electrical charge, got a magnetic moment, and it's a wave. Its wavelength goes as 1 over the square root of its energy. More energy, shorter wavelength. That's all you need to remember. We know this is true. You can do experiments where you generate electrons all of the same energy, keep E the same, then shoot them through 2 slits. If they're waves, as they exit on the other side, the waves exiting from this slit will interfere with the waves exiting from that slit. The interference pattern will have maxima in some directions, and it'll have null minima in other directions. So according to this theory, if electrons are waves and you shoot them through these 2 slits, then as they arrive in your detector, the probability of arrival here should be high, here should be 0, here should be high, etc. And nowadays, of course, you can do that experiment. You can capture electrons one at a time, and their probability of arrival is given exactly by the Schrödinger equation. We've known this for at least 85 years as an empirical fact of nature. However, to image this thing, has been a challenge which has been around for many decades. It's only in the last 10 to 15 years that it was possible to image the probability of those waves themselves. That's what we're here to talk about. Okay. Now, oops, that doesn't look good. Okay. Suppose you have some free electrons. They have a wavelength. The easiest way for us to parameterize them in terms of their momentum, p, is to say that it's Planck's constant divided by the wavelength, lambda. So k is proportional to 1 over lambda. It's the wave number. For long wavelength waves, k is very small. For short wavelength waves, k is very high. Now in the classical world, the energy is p squared over 2m. So it goes as the wave number squared. Long wavelengths have low energy. Short wavelengths have high energy. That's what you need to remember. Now that's true for free particles. In materials, the thing we're interested in to utilize for the basis of our civilization actually, in materials, not only do you have these waves, but you actually have the constituent material in which the wave is traveling. Let's say a crystal. In the crystal, the atoms are separated by a certain distance. 1 over that distance, 2 pi over that distance, is like a wavelength. If you consider the distance between the atoms to be a special wavelength, then you can represent it in this space as 2 pi over that distance. That distance sets the some very particular wave vectors and energies for electrons in a real crystalline material. Now, if there's an atom at each site, the nucleus is positively charged. The electrons are negatively charged. They'll interact with the nuclei, as Felix Bloch first showed about 75 years ago. Once this happens, the nice smooth curve of energy versus momentum for these quantum mechanical objects is broken up by these energy gaps. There are regions, there are wavelengths or wave vectors for which at some energy there's no solution. Those are the energy gaps which are the basis of our ability to control the properties of materials. Now if you put electrons into this compound, suppose you put an odd number of electrons per nucleus. You put 2 electrons into these states, and because they're fermions, you don't put them all into the lowest energy state. You have to keep filling up. As you put each electron in, you have to keep filling up to higher and higher energies. If you put in an odd number of electrons, then the highest energy state and its associated wave vector, that's called the Fermi energy and the Fermi wave vector, are somewhere in the middle of one of these bands. Then you have a metal. If you put an even number of electrons in, let's say here, 2, then the highest filled state would be on the edge of one of these energy gaps, and then you'd have an insulator. And a semiconductor is some complicated mishmash between those 2 limits, which I don't propose to discuss. However, this Fermi surface is really important. It's a theoretical surface in a 3-dimensional space that tells for all shorter wave vectors or longer wavelengths, there are occupied electronic states, and for all longer wave vectors or shorter wavelengths, the states are empty. It cuts off the filled states from the empty states. That's what the Fermi surface is. Now, on the basis of this set of ideas, we form our modern so-called civilization. We use materials whose band structure we know, controlling the amount of electrons on board, to produce insulators, conductors, semiconductors, and very complicated devices that use mixtures of those states in their operation. At the level of physics, we're dealing with a picture where we have independent electrons, each of which has a little magnetic moment, and then the Schrödinger equation describes their wave-like properties, and then there's another theory called Landau-Fermi liquid theory, which shows why, under some circumstances, you can consider these electrons to be independent of each other. They just move through the crystal and ignore their colleagues. All right, so here's some conventional electronic matter. Conductor, that's gold. That's Shoshank, the first signet ring. He's the guy who invaded Jerusalem about 3,000 years ago. So we've used metal for around 7,000 years in our technology basis. Here's an insulator. Here's a ferromagnet. It's lodestone. Chinese have at least been aware of that for about 3,000 years. In the Western society, for more than 1,000 years, we've used magnetic materials. Semiconductor, Michael Faraday discovered semiconductors in 1840, but they didn't become economically important until around 1960, as you all know. This one, ferro and piezoelectrics. Many people, even physicists, are not very well aware of these compounds, but they're tremendously widely used in our technology base. They're everywhere. All kinds of electrical and electrostatic actuators use piezoelectrics. And finally, superconductors fall into the same category. I'll tell you more about them, but they just involve free electrons moving in a very special way through a crystalline material. I'd call this stuff conventional electronic matter. That's about all we have. Now, we have other kinds of amorphous matter. We have glasses, we have biological matter, we have other kinds of matter about which I know very little and which I don't propose to discuss here. I'm primarily discussing crystalline matter and its electronic properties. But given that category, this is all we have to a first approximation. If you look in a graduate textbook, yes?
Could you amplify on what a magnetic moment is?
So a magnetic moment, you know what a bar magnet is? So the property of that bar magnet, okay, that it feels a force in the presence of a magnetic field, that property is called a magnetic moment. It just means the thing is a little magnet. So the electron is like a magnet which is 10 to the minus 24 times weaker than a regular magnet. Thank you. That's what causes this stuff to be magnetic. Okay. Now, are there other states of electronic matter? Are there other conceivable states of electronic matter? What's the rule that prevents us from having a whole bunch of other complicated forms of electronic matter? Well, that's a question I want you to think about. Okay? Now I'll give you a little bit of context for that question. Frontiers of quantum matter research, the areas where I try to make a contribution. Here we are again. Imagine now that you're allowed to make a crystal, let's say with any 5 elements. Right, that wouldn't work. This one would work. Lutetium would work. I give you 5 elements. There's about 100 of them. So if you can choose 5 arbitrary elements, there's 100 of them. That's 10 to the 10 permutations. 10 billion. So you could make 10 billion compounds out of those 5 elements. Actually, there's a whole variety of crystal symmetries and interpermutations for each crystal structure. So in fact, you could make more like 10 to the 12 compounds from those 5 elements. 10 to the 12. 1,000 billion new compounds. Okay. That's what I mean by untold possibilities for new materials. How many of those compounds have we made and studied? It's less than 100,000. The vast frontier of unknown properties of materials has not been explored. Okay? And they could have properties we can't even imagine. Here's some I study, and they look pretty damn complicated. And I just show you this to show that we do study materials of this complexity with multiple different exotic elements in the unit cell, and they do have very strange properties that we find hard to understand. So my argument here is true. There are many, many, many possible compounds available, and they could have many strange properties. All right, so could we have other states of electronic matter? Okay, so now you would say, let's go to our high-powered condensed matter theorists, okay, saving those who are in the audience here, and ask, if I take 5 of these elements and put them together in a crystal, what will be the properties of the electronic matter in that crystal? Well, we have no idea. There's no predictive theory for what state of matter will exist in any of these complex novel compounds. At present, they're found by the genius of material scientists, which is certainly, I don't understand how they do it. They choose a certain palette of atoms, they put them together, and boom, they discover new materials. But it's not based on a formal logical structure where you write the Hamiltonian, solve for the new material, and predict its properties. Nobody knows how to do that. Yes?
If you were to choose fewer elements,
yeah.
would you be able to have a predictive theory?
Yeah, so great question. So most of our semiconductors are made of 2 elements, like gallium arsenide. We have very good predictive power for most materials which are binaries. Ternaries, where you have 3 elements, we have poor but non-zero predictive power. By the time you get up to these kind of things, no one has any idea how to predict what's going to happen. Okay. All right. Now, let us consider an example of a possible new state of electronic matter. Not in the textbooks. Even today, not in the textbooks. It's too new. What I want to consider is electronic liquid crystals. Okay, see this stuff? You're probably familiar with it. It's called steam. Okay? And it's an isotropic fluid. It doesn't break any rotational or translational symmetries. It's just a fluid which has no other strange properties. However, and most of you know this, if you take steam and condense it into a strongly interacting form, namely water, it has very strange properties. Very hard to understand. This is one of the most difficult materials to understand, actually. We really don't have a predictive theory for how water works. But all you did is take the same constituents and make them interact more strongly to get this liquid state. Now, if you take the same guys and make them interact even more strongly, you might guess that the next state you would get would be a solid. And for those of us who live in Ithaca, we're very familiar with that solid. It's called ice. However, that deduction would be wrong. There's another state which can exist. It's a liquid crystal state. Liquid crystals are fluids which nevertheless break symmetries as if they were solids. They're a very exotic and fascinating state of conventional matter. This has nothing to do with electronic matter. This is a property of just conventional liquid crystals. Liquid crystals now form a key basis for our whole civilization. The role that mud bricks formed for the Sumerians and papyrus formed for the Egyptians and vellum for the Romans and paper until about 10 years ago is now formed by liquid crystals for our society. Our ability to understand and control these liquid crystal states is extremely important, and they're dually important because they're malleable. You can get them to change from one state to the other without too much perturbation. And of course, they're worth a tremendous amount of money. There's 2 types of liquid crystals, and I need you to remember this. One type is called a nematic. A nematic liquid crystal is a situation where all the molecules are aligned in the same direction, but no other symmetry is broken. They don't make a wave, they don't do anything. They just all line up head to toe in the same direction. It's like sunbathers on a beach in the south of France. For some reason I've never understood, they all line up in the same direction. They're in a nematic state. The other state is a smectic state. A smectic state, each molecule orients in the same direction, but then they make a periodic array. They make a wave-like state. Okay, so nematic, they're all aligned in one direction. We say they break rotational symmetry. Smectic, they're all aligned, but they're also periodic in space. Okay. This is Pierre-Gilles Dijen. Liquid crystals were discovered in the 1890s. Cholesteric liquid crystals were discovered in the 1890s. Nobody could understand them or predict their properties or use them until Dijen solved the problem in 1974, for which he subsequently received the Nobel Prize in Physics. So the key thing in solving the problem was genius. The second key thing was that by the early 1970s, phase contrast microscopes made it possible to visualize liquid crystals and to see what the arrangements actually were in real space. The visualization was critical to Dijen's discovery of how these compounds work. His discovery is the physical basis for our control over liquid crystals in our industry and in our civilization. And most unfortunately, he died as a relatively young man about 5 years ago. So here's the argument. Weak interactions, homogeneous fluid. Stronger interactions, exotic fluid. Stronger but not ultimate interactions, liquid crystal. Okay, now, suppose I give you a weakly interacting gas of electrons. There's probably a kilometer of those copper wires. Well, there's many kilometers in this building, and there are millions of kilometers in Manhattan of these copper wires. They contain a fluid of electrons which is essentially homogeneous. It doesn't have any exotic properties. It's like steam for electrons. Now, if you increase the interaction between the electrons, and we now know how to do that, there are exotic heavy electron fluids which come into existence. And I work on that problem as well, but I won't have time to talk about it today. They're fascinating. They're the water of the electronic world. They have many weird properties. But now, if you increase the interactions between the electrons a little bit more,
Sorry.
what do you get?
How do you actually do this?
Say again?
How do you actually increase the interactions?
Okay. So in the intermediate case, it's via a property of the stationary atoms in the crystal. You actually make an interaction between each delocalized electron and the stationary atoms in the crystal. When you put that term into the theory, you find out that the electrons here are strongly interacting. And in this case, you could take a material which doesn't satisfy Landau-Fermi liquid theory. I'm sorry to put it in those terms, but it means you can't assume that the electrons essentially ignore each other. Each one is aware of every other one. Okay? There are many, many materials like that. We just don't use them or study them because they're too difficult to understand. Okay. So here, the hypothesis might be that there could be an electronic liquid crystal phase. So this is Eduardo Fredkin, Steve Kivelson. Eduardo is from the University of Illinois. Kivelson, when he made this proposal, was at Stony Brook, but now he's a traitor. He's at Stanford. So, and they made this proposal with Vic Emery, who, as the professionals know in this audience, was a great theoretical physicist at Brookhaven National Lab. They proposed that if you take materials where Landau-Fermi liquid theory doesn't apply, namely the electrons are all aware of each other all the time, you can get electronic liquid crystal states. This proposal was only made about 15 years ago, and at the time it was regarded as somewhere between ambitious, somewhere between extremely ambitious and insane, I would say, in that window. But I remember very clearly I was visiting Steve, and oh, I forgot to say, I had never worked in this field before. I worked in a completely different field when I was at Berkeley. So I was visiting Steve, and he made this pitch to me. He said, look, there are these new states of matter which could be found if you go to these so-called doped Mott insulator phases and search for electronic liquid crystals. And I was strongly motivated by that, and I thank Steve for that proposal. Because now I want to tell you, how would you visualize electronic matter, quantum mechanical matter at the atomic scale? Okay, well, you use a scanning tunneling microscope. So a scanning tunneling microscope is an object with a sharp needle, metallic needle. It's got one atom on the end. You bring that needle in close proximity to the material you want to study, and you scan it back and forth over that surface, like an old gramophone scans its needle over the surface of the disk. Now, one thing you might think looking at this cartoon is, by God, this must be hard to do. One atom on the end of the tip. But if there were any Greek philosophers in the audience, they would tell you that this is trivial. If atoms exist, there's one atom on the end of every object. And that's actually true. It's actually very easy to make these tips with one atom on the end. The hard part is to raster this object over the surface so that it maintains a distance of order 1 angstrom, 10 to the minus 10 meters, without crashing into the surface. The way you do that is you apply a voltage between this conductor and that conductor, and electrons tunnel through the vacuum in between. This is quantum tunneling of electrons. You measure the tunnel current, then you feedback. As you raster over the surface, you keep the tunnel current constant. An image of the feedback voltage is, you can show, an image of where the atoms are. And this is a real one. This is an image of selenium atoms, as you can no doubt tell by looking at it. So these machines already were commercialized by the 1990s, and they're wonderful for taking pictures of where atoms are in a material. These are bismuth atoms. These are calcium atoms. These are strontium atoms. And these are very interesting. They're uranium atoms. These machines, though, your commercial scanning tunneling microscope, images where the atoms are. It does not image the electronic matter. And it's a particularly poignant example of the failure of that approach to this system is to consider these 4 compounds. All 4 of them have exotic electronic liquid crystal states in them which cannot be detected by this scheme. You just see where the nuclei are, basically. Yes?
Well, if you're using electron flow, aren't you really measuring the outermost shells of each of the atoms that you're scanning over?
It depends on what energy you're using, but to first order, yes. So you're detecting where the bound electrons are in one of those shells, but you're not detecting where the strongly interacting but otherwise free electrons are inside the material. Okay. Now, there's another thing you could measure. So you're going to measure the current traveling through this tunnel junction as a function of the voltage that you apply between the 2 pieces of metal. And now you take the derivative, d current, d voltage, that's called the differential conductance, and you can plot that as a function of the voltage, and it'll be some complicated curve. Now you can show from theory that this differential conductance is proportional to psi squared, the wave function squared, for the states at energy E, which is set by the voltage that you use, and at the location where you make the measurement. Giever got the Nobel Prize in 1974 for showing this is true. The differential conductance is a measure of Max Born's psi squared at the energy at which you do the tunneling. Any questions about that? That's the key thing we're going to use now. All right. Now here's a simple idea. Take some complicated surface and put your STM tip up there in the left-hand corner and measure the differential conductance. That's the IdV versus V. It's a curve. And assign that curve to the first atom up there in the left-hand corner. Okay? That's a simple idea. Now you know psi squared at that first atom. Okay, so the rest is logically trivial. Why don't you just measure that at every atom? Move to the second atom, do the same thing. Move to the third atom, do the same thing. There's about 60,000 atoms in this field of view. 60,000 measurements later, you have a complete map of psi squared, Max Born's wave function squared, versus energy, because your spectrum has energy, and versus location. It's an image of psi squared resolved by energy and resolved by location. And since you resolve by energy, I have to show you a movie to show you what it looks like at different energies. That's the energy of the electrons we're looking at. As we scan through the energies, you see the wave functions are different at every energy. Those are some individual impurity atoms that just flashed by. But as we go through the energies, you see all kinds of different things happening. Now, let's see. Okay, let's go back. I demonstrated this in 1999. I sent the first major paper to Nature in 2000. It was unpublishable, completely unpublishable. And the reason was that most people have not taken on board that in quantum mechanics, completely different things can occur at the same location, provided the energies are different. We all learned that in school, but to see it in a movie was too disconcerting. So it took a long time to publish the first paper. Yeah?
Fairly pedestrian question.
Yeah.
As the outside factors, are any...
Please use the microphone when asking questions.
Are there the outside factors of getting this information any detriment to the information?
Yeah, the
that you
laboratory
get?
is critical.
I was going to say, because it seems like it's in a vacuum, or
No, that's a great question. You see this argument I made here, just measure this spectrum at every atom for, say, 50,000 atoms. So I had never worked in this field, okay? So it was well known that this was impossible, okay? But I didn't know that. I'll tell you, that's the next thing. Any other questions? So this is our main observable. psi squared resolved by energy and location. Max Born wave function squared. Okay. This is extremely difficult. If you take 512 by 512, and then you take 200 data points in each spectrum, that's 50 million measurements. If you want to make 50 million measurements in one day, even in Manhattan, you've only got 2 milliseconds per measurement. In those 2 milliseconds, you need to get a signal to noise of around 100 in order to end up with a useful piece of information. So the main difficulty is that if this tip, I did the calculation in my naivete, I did the calculation to figure out how much random motion could this tip have and this still be possible. And the answer is the random motion of the tip relative to the surface at every atom. So you take it and put it at one atom, park it at that location. The random motion should be less than a femtometer, less than the diameter of the nucleus. And you get a fraction of a second to make the measurement. Then you move it to the next atom, park it, and then stabilize it so that the random motion is less than the diameter of a nucleus. It was well known that this was impossible. There are famous papers showing that this is impossible. But like I say, I didn't know that. So I just took a boneheaded, brute force view of this situation. I said, what laboratory environment would be required so that in a mechanical object in the laboratory, the relative motion of two particles, two objects inside the same mechanical assembly, would be less than a femtometer. So this is how we did it eventually. You take an underground reinforced concrete vault, basically a cave. And in the cave you put acoustic absorbing material. Already it'll be so quiet that your ears will start to ring. Then inside the cave you put a commercial acoustic room. This is like a room that musicians use when they're making recordings. And then inside your commercial acoustic room you put an ultra low vibration table, and suspended from the table you put a refrigerator which can cool the microscope down to 1 Kelvin, minus 272 degrees centigrade. And furthermore, you take your acoustic recording room with its ultra low vibration table and millikelvin refrigerator, and you also put it on a bunch of giant pistons whose job it is to isolate the whole room from the external world. Okay, so I had figured out that this was possible in 1999. The first movie, like the one I show you here, this one took 8 hours. The first movie took about 3 months because we didn't have the correct laboratory environment. So the institution I was at the time, I went to see the dean and said, gosh, this is a great opportunity to invent a new technology, blah, 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 blah. He just told me to get lost, which I did. So I moved to Cornell. I knew Bob Richardson, who was then the vice provost of Cornell, and I told him this story. He looked at the equations. He said, okay, let's go ahead. So this is the A corridor of Clark Hall in Cornell. Our colleagues are over here, and they didn't want to have any part of this process. So in order to build these ultra-low vibration labs, we had to dig down on the outside, like tomb robbers, and cut a hole in the underground wall, and then come in and dig down another story. So eventually we ended up with something which is like a small piece of the Channel Tunnel. And into that place we put 4 ultra-low vibration labs, and today 3 of them are being used for these quantum visualization machines. 4th one's being used for new gravity research, which I won't have time to discuss here. We have visitors from all over the world. Typically they have some weird material that no one can understand, and they would like an image of the electronic structure, so that instead of decades of theory and measurement and theory and measurement, 8 hours later you have a picture of what the wave functions are doing. Say again?
What did you do that made the impossible possible?
So I suppressed the vibrational noise. Very good question. The vibrational noise between here, which is approximately what it would be in the hallway outside. The floor, the walls and the floor are moving by a few microns, just due to acoustic noise and traffic noise and so on. We suppressed it from here to inside here by about 9 orders of magnitude. That was the mechanical part. And we suppressed the thermal noise from room temperature down to sub-Kelvin temperatures, maybe 4 orders of magnitude. Inside our machines here, the experimental environment is between 1,000 and 10,000 times more quiet than the end station of LIGO. With apologies to any gravitational physicists in the audience, these are much quieter. That's because they're at millikelvin. Okay. All right, now let's do some physics. How would you image these electron waves? Okay, imagine I have a material and it has an impurity atom in it. Okay? Now, unless you've been in my business for a while, you might say, why is there an impurity atom in my material? But all materials are jam-packed with impurity atoms. They're completely unavoidable. There's only one material in nature that has no impurity atoms, and it's liquid helium-3. Everything else has impurities. So there's an impurity atom here. Now bring one of the Schrödinger waves of the electron in. It's got a certain wavelength. The wavelength, so the wave number is inverse proportional to the wavelength. So we know the wave number. It hits the atom and it scatters. Now the way quantum mechanics works, you have to add these two guys together and then square to find the amplitude. When you add these two guys and square, you get something of a different wavelength. Okay? In fact, it's half the wavelength. Okay? Or the wave vector of the modulation here is twice the wave vector of the state which created it. Friedel predicted that around 1956. It took until the early 2000s to see this thing clearly in real space. At every impurity atom, if you're not an aficionado of quantum mechanics, think of a lighthouse in the middle of the ocean. Big ocean waves are coming in and hitting it, and the response is a standing wave near the lighthouse, which is circularly symmetric and has a certain wavelength associated to the wavelength of the incoming waves. Okay, now we can measure this stuff. This is psi squared of the electrons. That's what we built the machine to measure. So we can measure this image as it is, but it's a mess. So now what you do is take the Fourier transform of this image. It will extract the value of whatever waves exist in the image. Here, all the waves have the same wavelength. So in Fourier space, this complicated image will turn into a circle. The radius of the circle is the q vector of those waves, 2 pi over their wavelength. Okay? Now, q is related to k of the electrons, which existed in the compound. So you measure that q, and you can divide it by 2, and that'll tell you the two values of k which these electrons had, plus and minus k. For the physicists in the audience, you scatter from plus k minus minus k, you get 2k. All right? So that's cool as a cartoon. Now, in terms of using the machine, you image this differential conductance at every energy, take the Fourier transform at every energy, and extract the band structure at every energy, like this. So there you have it. You can just image the Max Born waves as they exist in this and more or less any metallic material which has a good surface. So this was just a cartoon to show you what's going on. Here's a real material, a very complicated high TC superconductor. And if I show you the image of the waves in real space, I already showed it to you. It's a horrible, god-awful mess. And one thing I have learned is that quantum waves in real space are pretty much always a horrible, god-awful mess. However, if you take the Fourier transform, picks out the wavelengths, it's a beautiful symmetric set of wavelengths which change with energy. We now know in excellent agreement with theory. That's one type of compound. Here's a different. Oh, sorry. These were the first wave function movies ever made for the copper superconductors. These are the first wave function movies ever made for the iron superconductors. If I show you the wave functions, they're a god-awful mess. Very weird. If I show you the Fourier transform of the same data set, it's beautifully symmetric. It has 3 bands, which we can diagnose with great precision. Here's these heavy fermion compounds. People had been predicting the wave properties of these compounds since the 1970s. No one had even known whether the theoretical predictions are correct. These were the first movies of a heavy fermion wave function. You see the waves on the left-hand side. You see the Fourier transform on the right-hand side. It's very nicely symmetric. It gives us all the information we need. Okay, so this is a very powerful technique. It's interesting now. I'm getting on in my career a little bit. When we first introduced this scheme, we called it quasi-particle interference imaging for technical reasons, QPI. So now,
I have
yeah.
one small question. Is this the best way we have of actually visualizing band diagrams today?
So you can use photo emission to measure the band structure of compounds. The energy resolution of photo emission is a few milli-electron volts. Our energy resolution is between 100 and 1,000 times better. So if you need very high precision, this is the best way. If you need a kind of quick and dirty analysis, photo emission is the best way. Very good question. Yes, quasi-particle interference imaging, QPI. So now I get graduate students these days who blithely tell me that, we should just use QPI to solve this problem. And I ask them, well, where did QPI come from? They have no idea. So it's lost in history. Okay. All right, 20 minutes to go. Now I want to tell you the active area of my research, but it's closely related to the set of ideas that I've been introducing to you. High temperature superconductivity. So superconductivity is a state of electronic matter where electrical current can flow in a perfectly dissipation-less way. So you can have dissipation-less electrical and electronic systems. Discovered, so this is 4.2 Kelvin, minus 269 centigrade. It was discovered by Kamerlingh Onus a little bit over 100 years ago, I guess 104 years ago, in Leiden. Now, what is a superconductor? So here's my gas of electrons. Here's its Fermi surface. But it's unstable. Cooper showed that it's unstable. There's a lower energy state. It's a state where each electron binds to another electron to make a Cooper pair. He cleverly called it a Cooper pair. And when it does so, the binding energy per electron for the Cooper pair, this energy, appears in momentum space as a gap, an opening in the spectrum of excitations at the Fermi energy. So we've understood this for 50 or 60 years. We know the theory as well. It's the Bardeen-Cooper-Schrieffer theory, for which they shared the Nobel Prize. In any case, what's going on here is you have a fluid of very weakly interacting electrons. At a low enough temperature, each electron finds its mate, which has opposite spin and opposite momentum, and makes a new quantum mechanical bound state. That's the Cooper pair. And then those new states condense into a fluid which has no dissipation. It's an electronic superfluid, or a superconductor. Now here's a graph of the critical temperature below which you have to go before the material is superconducting. This is in Kelvin, so this is 4 Kelvin, minus 269 centigrade. And this unit here is in years. So the rate at which the critical temperature of superconductors was rising for the first 7 decades of study of this material was such that to get to room temperature, we'd have to wait until the year 3500. Now, the youngest people in this audience probably still feel like they could wait until the year 3500, but I do not. So to get out of this trap, we need a new class of materials. Why? There are many, many, many persuasive reasons why we need superconductivity in our technological basis for our civilization. We have terrible problems with efficiency and stability of our power network in North America, and even worse in other parts of the world. Many of them would be solved automatically by using superconducting power lines. Power bottlenecks. The worst power bottleneck in the United States of America is right here in Manhattan. The rate at which power usage per square meter is rising is such that by around 2035, nobody knows a way to deliver enough power to Manhattan. That's a really serious problem. The DOE has a whole program to figure out what to do with sending enough power to Manhattan. However, and of course, one way you could do it is you could dig up all the streets, pull out the old copper wires, and put in a new system. But I'm sure nobody in this audience would wish to live through the digging up of all the streets in Manhattan. So there's another way. If you had superconducting power cables, for the same diameter, they carry between 30 and 100 times as much power. You could pull out the copper cables, push in superconducting cables, and solve that problem. And that's a very serious proposal. People have been trying it in other big cities like in Seoul. We're trying to have renewable energy distributed at all kinds of different locations throughout our continent. One big problem, though, is that you can't have a new high voltage power line for every solar farm. It can never happen. It's much too expensive and people will never put up with it. You need a way of delivering all this power through a more or less invisible network. The easiest way to do that would be a superconducting network. We need much more efficient rotating machines. A superconducting windmill farm for power would be about 10 times more efficient. Information technology, the largest rate of increase of energy of any area in our society is in information technology. The reason why Google can answer your question before you finish typing is A, they know a great deal about you, but B, they have enormous server farms all over the world with hundreds of millions of computers that use an enormous amount of energy, so much so that you can see the server farms from space with infrared. Superconducting information technology would not generate any heat, and it would be about 1,000 times faster. So here it would make an enormous difference. Our high energy colleagues need compact accelerators for next generation linear accelerators. The best way to do that is with superconducting resonators. We need high field magnets. There are many important medical applications. Before the Second World War, there were 12 trains to Ithaca every day, and now the number of passenger trains to Ithaca every year is 0. So I would very much like to have an efficient transport network in the Northeast. So here's our hope. There are 2 classes of compounds, one discovered by Alex Müller and the other by Hosono-san, which are high temperature superconductors. I'll tell you more about them in a second. So the copper-based ones were discovered here around 1986, and the iron-based ones 20 years ago, about 2006. And these are the critical temperatures of various copper-based compounds, and these are the critical temperatures of various iron-based compounds. So you can extrapolate those lines. It's a useful thing to do in a proposal, and say that room temperature superconductivity is somewhere around the corner. I believe it is. Now, where's it coming from? These things are very strange materials. They're antiferromagnets. This copper atom has its magnetic moment pointing in one direction, opposite, opposite, opposite. The iron one's the same. They're antiferromagnets. These guys point one way, these guys point the other way. They're also two-dimensional, very two-dimensional materials. And they're not superconducting a priori. Both of those things are two-dimensional antiferromagnets. To turn them into superconductors, you have to change the number of electrons inside the compound. You have to increase the electron density. There are chemical and physical ways of doing that. When you increase the electron density, you destroy the magnetism. Antiferromagnetism disappears. And then high temperature superconductivity appears. Similarly, when you increase the electron density in the iron compounds, antiferromagnetism disappears, the high temperature superconductivity appears. So clearly, there are many similarities in these 2 phase diagrams which lead physicists to believe that there's one fundamental process going on here. However, this state is still unidentified. Most people would say, I'd say I know what it is, but most other people would say this is unidentified. This state was unidentified for a long time, but we do know what it is now. There are strange electronic states in these compounds which really had no precedent. So here's a cartoon-like view of the situation. You have an antiferromagnet. You change the number of electrons in the crystal. eventually you reach a point where the antiferromagnet is gone and you have Cooper pairs of a high temperature superconductor. The hypothesis is that there's another intermediate phase. Kivelson calls it an intertwined phase. You can use the I for intertwined, or you can just use I for intermediate. But the generic proposal is that there's another intermediate phase between these two states, and that phase is an electronic liquid crystal. That was their proposal, Fradkin and Kivelson, 15 years ago. So let's take a look at the iron superconductors by visualizing the electronic structure. So again, this is the critical temperature of the superconductor. This is the number of additional electrons in the crystal. As we put in the electrons, we diminish the magnetism, we increase the superconductivity. We want to know what's causing the superconductivity, and we want to know, is this an electronic liquid crystal state? So here's an image, actually this is the first image, of a stable surface of an iron superconductor. It's calcium, iron to arsenic 2 for the experts. And we know where all the atoms are on this surface. Here's a related image, same thing, surface of the crystal. Here's an image of the wave functions. This is the first movie of the wave functions in the non-superconducting parent state of these compounds, the state which disappears in order for the superconductivity to appear. If I run this movie, it's pretty unprepossessing. If you're careful, you can see the wavelength increasing in the vertical direction, but not in the horizontal direction. My graduate student at the time, Milan Allen, was sure that his thesis was doomed when he saw this movie. However, if you take the Fourier transform, it's only got 2 wave vectors, and they evolve smoothly only in one direction. Okay? The crystal symmetry is 4-fold, but the direction that the waves are evolving is only in one direction. Now that same graduate student is a professor at Delft, so he was wrong. So we also were able to see that there were 8 unit cell static little nematogens in the crystal, and that they were all pointing in the same direction. I remind you that that's what you're looking for if you want to find a nematic liquid crystal. Same objects, all pointing in the same direction, but without any order. Finally, they were able to find, my students were able to find a twin boundary, which is along here. At that boundary, the crystal symmetry rotates from one direction, from being, let's say, east-west, to the other direction being north-south. We could show that the nematogens were aligned in one direction on one side and in the other direction on the other side. Furthermore, we could show that the wave-like, Born wave-like states were dispersing in one direction on this side and in a different direction on that side. So we're able to show that all the necessary characteristics of an electronic nematic state exist in the parent state of the iron superconductors. Boy, this was hard to publish, I can tell you. In the end of 2009, there was very few people, except for a handful of theorists, who were willing to subscribe to the idea that the superconductivity came from a nematic state. However, in the end, we succeeded after about a year of fighting. And now, if you look in the literature, you'll find maybe 10,000 papers about the nematic state of the iron pnictides. It's absolutely crucial thing, the parent state from which the superconductivity comes. Now, we can also see the superconductivity. This is a crystal structure. We can see the energy gap. That's the energy holding the Cooper pairs together. And I already showed you, we can see the wave functions of this iron superconductor. They're a horrible mess. We can see them in Fourier space. They're beautifully well organized. There are 3 bands, 1, 2, 3. And from that, we can deduce what the momentum space structure is of the energy gap. Now we know not only about the nematic phase, but we know about the formation of the Cooper pairs. And we can say that here's the Fermi surface, here's the energy gap, here's the nematic phase. They exist as predicted by the Fradkin-Kivelson style theories. Schematically, there is a nematic phase here in the iron superconductors. Now you could, okay, I won't prejudge that. Just keep this picture in your mind and let's look and see at the copper superconductors. Okay, copper-based. So again, we'd like to know what's forming the Cooper pairing and what weird state is over here. Gave it away. So here's a picture of where the bismuth atoms are. Each copper atom is underneath one of these bismuth atoms. If I take a picture of the static electronic structure in the same field of view, it looks like this. It's amazingly complicated. It's like a bad tweed in some way, but it's not completely disordered. The human eye will pick out well-ordered objects on a small scale in these images. And I'm going to tell you what those objects are in a second. Now you take the Fourier transform of this thing, it has two periodic structures. One, the red circles, is just the periodicity of the crystal. It has to be there. The other one, the blue one, is kind of like the wavelength of these things. There's one unit, there's another unit, there's another unit. There's some kind of very rough and ready wavelength modulation of these states. So quickly we took a look at the peaks, which are periodic with the crystal. We were able to show that in Fourier space, the peak in one direction is completely different than the peak in another direction. That formally tells us that there's an electronic nematic state also in the parent state of the iron superconductors. It's a breaking of symmetry inside the unit cell. For the experts, there's a copper and 2 oxygen atoms in every unit cell. Formally, there's no reason why the state of oxygen pointing that way is west, I guess. No, that way is south. So oxygen this way and oxygen this way should be in the same state. But what this analysis shows is that they're always in a different state. So it breaks rotational symmetry. It's an electronic nematic. Second one, we can take an image, we can look at the wavelengths of those blue things. So now I want to zoom in a little bit and let you see what this very exotic state of electronic matter looks like. Each dot here is at the location of a copper atom in the copper superconductors. And now I'll show you a movie of what the Max Born wave functions look like. They hardly change with energy at high energy. At low energy, electrons are free to move, so their wavelength changes with energy. Let's go back to high energy. Here you see a periodic structure appearing in these crystals. Not in where the atoms are, just in where the electrons are. We had some, let's see, we first found this thing in 2007. T. Morris Rice, who is a compatriot of mine, he's Irish and a very famous condensed matter physicist. He was the referee for this paper, and he rejected it the first time. He forced us to show that in completely different cuprates, you get the same result. So he did me a great favor, because in completely different cuprates, you get the same result. Very good referee. There's a periodic structure in the electronic wave functions, and it also breaks rotational symmetry. Okay? Now let's zoom in a little bit. We know where all the atoms are. Each black dot is a copper atom. Each blue dot is an oxygen atom. So there's a copper there. This oxygen and that oxygen, this oxygen and that oxygen are in a completely different state than this oxygen and that oxygen. And that's true globally. There's a spontaneous breaking of rotational symmetry inside every unit cell. At last, you can look at these ordered unidirectional objects. They're the same in different compounds. We now know this to be true in a total of 4 compounds. What produces this weird state in the wave function? So that really kept me awake nights for about 7 years to try and figure that out. Last year, we figured it out. There's a density wave traveling in this direction. And so normally you would expect it to look like, let's say, an ocean wave. If I have an ocean, so there's 2 degrees of freedom in every unit cell. There's 1 copper pointing south and 1 copper pointing east. So a conventional wave, if the condition of the copper was changing, 1 oxygen pointing south and 1 oxygen pointing east. If the condition of these 2 atoms was undergoing a modulation, you would expect them to do the same thing. That's called an S-symmetry density wave, been known since the 1970s. But there's an alternative. They can be out of phase. they can do this. That's called a D-symmetry density wave. Been predicted in textbooks since the 1970s. This is the first D-symmetry density wave discovered. And amazingly, it exists in the cuprate parent state to the superconductor. So that was an exciting discovery last year. We also can see the superconductivity. I won't bore you with the details, but we know what the superconducting energy gap is in these compounds. So in summary, we know how the superconductor is formed. We know that there's a smectic state. This is a state where you have some co-aligned objects, but they're periodic in space. And we also know that there's a nematic state in the parent to the superconductor. So that's the conclusion. There's a nematic plus a D-symmetry smectic in the parent state to the copper superconductors. All right, what's next? Okay, so this is our objective, to give you room temperature superconductivity. In order to do that, we have to find out what should we do to this guy in order to improve that guy. So you might think they're enemies, okay? Let's just figure out materials where we get rid of this guy, and maybe the superconductivity will become more robust. It only has to strengthen in terms of energy by a factor of 2, and we'll have room temperature superconductivity. It's an appealing prospect. What should we do to the copper superconductors? We have this weird state. It's impacting the superconductivity. Let's get rid of this state and amplify the superconductor. That's traditional solid state physics. You would find that argument in the textbooks going back to the 1950s. But there's another possibility. These two guys, this stuff and this stuff, can be degenerate solutions for the physicists in the audience of the same Hamiltonian. They can be like two different species of neutrinos. They're different solutions, but they're closely related to each other in energy. That would mean you're mixing two very exotic quantum mechanical states. So here's my last slide. About 3 weeks ago, we were able to find a certain set of wave vectors, or wavelengths, for the electrons in this compound, where by applying a magnetic field, we could convert the superconducting Cooper pairs into the density wave states at only these locations, and we could measure the mixing angle between the two states. So we don't think these two states are competing. We think they're almost degenerate solutions to the same Hamiltonian. That means that the problem we need to solve to get room temperature superconductivity is not to get rid of this stuff. It's to understand the fundamental Hamiltonian that is both producing this and the superconductivity, and then to control that in order to drive up the TC of the superconductor. Okay. There are many, many, many general applications of this approach to visualizing quantum electronic matter, which I don't work on. It's now, there are probably half a dozen or more of these labs in the world, and more being built all the time. But among the things you can do, you can image electronic disorder at the nanoscale. You can image the wave functions, the Born wave functions. You can image the effect of individual impurity. These are dopant atoms. You can image the heavy fermions. That's a strongly coupled electronic liquid. You can image other properties of superconductors. You can image electronic liquid crystal states. If you're a hardcore material scientist, you can image where every dopant atom is in the material to figure out what it does. And you can image many other things. I'm interested in room temperature superconductivity, but in many other fields now. Topological insulators, topological superconductors, ferromagnetic semiconductors, all kinds of other fields. This type of instrument is coming to the fore because it cuts short the traditional problem of condensed matter physics of have a new material, measure the resistivity and the heat capacity, write a theory, make some predictions, make another round of measurements, improve your theory, and so on and so on. It cuts that short by giving you a direct picture of what the eigenstates are, what the wave functions are in a given exotic material. Thanks very much.
Thank you so much for this wonderful talk. Are there any questions? Yes, please, but please use the microphone. It's right here. Yeah, you have